Hi everyone, I'm going to talk about bilateral trade with correlated values. This is a joint work with Shahar Dubzinski. In the bilateral trade problem, we have one seller who owns an item and a buyer who seeks to purchase it. We denote by B the value of the buyer for attaining the item, and by S the value of the seller for keeping the item. S and B are the private information of the two agents, and they are sampled from publicly known distributions. A common assumption is that the values are sampled from independent distributions. The value S is sampled from some distribution f of S, and B is sampled from some distribution f of B. And now an instance of the bilateral trade problem is going to be a tuple of these two distributions. A mechanism for an instance of the bilateral trade problem gets as an input the agent's reported values, S and B, and it returns an allocation and payment. We will focus on mechanisms that are deterministic, and so the allocation is either 1 if there is a trade or 0 if there is no trade. We will want mechanisms that are strongly budget balanced, and so it means that the amount that the buyer pays for the item is exactly equal to the amount that the seller gets for the item. Also, we want our mechanisms to be ex post individually rational. This will guarantee that no agent will regret participating in the mechanism. And it translates to requiring that the payment is at least the value of the seller and at most the value of the buyer. Finally, for incentive compatibility, there are two options here. The first one is dominant strategy incentive compatible, and it means that for every agent, no matter what the other agent reports, reporting his true value maximizes his profit. The second notion is Bayesian incentive compatible, and this is a relaxation of the first one. It means that for every agent, reporting his true value maximizes his expected profit, assuming the other agent reports his own value. Okay, so now for our objective, which is how we are going to measure the performance of our mechanism. Here there are two notions. The first one is welfare. And so the optimal welfare is the expected value of the maximum between B and S. And the welfare of a mechanism M is going to be the expected value of the agent who ends up with the item. We will mostly focus on welfare. And the second notion is called gains from trade, and it measures the expected improvement in the welfare that is caused by a trade. And the gains from trade of a mechanism is always equal to the welfare of this mechanism minus the expected value of the seller. Okay, so the optimal allocation for both welfare and gains from trade is going to be the same. This is the allocation that trades the item whenever the value of the buyer is larger than the value of the seller. However, for approximations, this is not the same. Approximating the gains from trade is a harder task than approximating the welfare. And so if we have a mechanism that gives an alpha approximation to the gains from trade, then we automatically get a mechanism that gives an alpha approximation to the welfare. And there are also two notions of optimality. We have the first best, which is what we described so far. And we have second best, which is the maximal value among all incentive-compatible, individually rational, and budget-balanced mechanisms. In our work, when we say opt, we mean the value of the first best. Now I'll mention some of the related work that is most relevant to ours. Meyerson and Satterwhite proved that even for independent distribution, exact maximization is not possible, under some very mild conditions on the distributions. And so in other words, the first best is not equal to the second best. And so people started considering approximations. Meyerson and Satterwhite also described the second best mechanism, which is very complex. In any case, this is only for independent distributions. Now I'll mention an important class of mechanisms called fixed price mechanisms. So a fixed price mechanism for an instance of the bilateral trade problem first observes the distributions, and then it decides on a price P. Now, we ask the agents for the reported values, S and B, And if the value of the seller is smaller than P, and the value of the buyer is larger than P, then there will be a trade. The item is transferred to the buyer, and P units of money are transferred from the buyer to the seller. However, if the value of the seller is larger than P, or the value of the buyer is smaller than P, then there will be no trade. Now, this class of mechanisms are important because they are simple mechanisms, but also this is actually the class of dominant strategy mechanisms. We have an equivalent between fixed price mechanisms and dominant strategy incentive compatible mechanisms in this setting. It was observed by Blumrosen and Dubzinski. So now, for approximating welfare for independent distributions, fixed price mechanisms are enough. They provide a good approximation. The first mechanism gave an approximation ratio of 2. It was later improved to 1.96, and then to E divided by E minus 1. And it seemed like maybe this is the right answer. However, it turns out that we can do slightly better. And quite recently, it was improved to an almost optimal ratio of 1.38. So this was for welfare, and now we'll talk about gains from trade for independent distributions. McAfee showed that under some conditions on the distribution, there exists a fixed price mechanism that gives an approximation ratio of 2 to the gains from trade. However, in general, this is not true, and no fixed price mechanism can provide a constant approximation to the gains from trade. This was shown by Blumrosen and Dubzinski. To overcome this, Blumrosen and Mizrahi suggested the seller offering mechanism, which I'll define next. So in the seller offering mechanism, the seller, after observing his own value S, makes a take it or leave it offer P of S to the buyer. Now observe that this mechanism is Bayesian incentive compatible for the seller. However, this is dominant strategy for the buyer, as the buyer can only accept or reject an offer. So what will be the price P of S that the seller will choose? It will be the price that maximizes his expected profit. So the seller expected profit is P, the payment he will get, times the probability of trade, plus S, his value, times the probability that there is no trade. Blumrosen and Mizrahi also showed that if the buyer's value is drawn from a distribution with monotone hazard rate, then the seller offering provides an E approximation to the gains from trade. Similarly, the buyer offering mechanism was defined. Now, in this mechanism, the buyer, after observing his own value B, makes a take it or leave it offer to the seller. And now the price, P of B, that the buyer will choose is going to be the price that maximizes the expected profit of the buyer. And the profit of the buyer is his value minus the payment times the probability of a trade. Building on these two mechanisms, the random offerer was defined. This mechanism runs with probability half the seller offering and with probability half the buyer offering. Brustal et al. Show that this mechanism provides a 2 approximation for the second best gains from trade. Deng et al. Showed that this mechanism actually provides a constant approximation to the first best. And their ratio was later improved to 3.15 by Fay. We also have a lower bound of 2 by Babayev, Dubzinski, and Kupfer. Okay, so just to recap what we have seen so far, for independent distributions, exact maximization is not possible. For the welfare benchmark, there is a fixed price mechanism that give a good approximation. The best one is 1.38. And for gains from trade, no fixed price mechanism can provide a constant approximation. However, the random offer mechanism can give a constant approximation. So now we are going to start talking about correlated distributions instead of independent ones. Very similarly, we have a seller who owns an item and a buyer who seeks to purchase it. The value of the buyer for retaining the item is B. The value of the seller for keeping the item is S. S and B are again private information of the two agents, and they are sampled from a publicly known distribution, but this time the distribution is allowed to be correlated. We have the same definitions for welfare and gains of trade as we had before. I will now state most of our results. They are for correlated distributions, deterministic mechanisms, and approximating the welfare. Okay, for the class of Bayesian mechanisms, we show an upper bound of E divided by E minus 1 and a lower bound of 1.34. We achieve the upper bound using the Bayer offering mechanism. As you recall, the Bayer offering mechanism is not completely Bayesian, as it is dominant strategy for one of the agents, for the seller, and it is Bayesian for the other, for the buyer. And so we define a class of such mechanisms that we call one-sided. There are mechanisms that are dominant strategy for one of the agents and Bayesian for the other. Now for this class of mechanisms, we show a matching lower bound of E divided by E minus 1. And so in this class, the Bayer offering is optimal. Next is the class of mechanisms that are dominant strategy for both agents. We show that no dominant strategy mechanism can provide a constant approximation to the welfare. This is in contrast to the independent case, where a dominant strategy mechanism provides a constant approximation and even the best known. Note that the best approximation for independent distribution is 1.38, which is quite close to the approximation we have for correlated distributions. So now, in the rest of the talk, I'm going to talk about this result. Next, we are going to give some intuition to our main result, that the Bayer offering mechanism provides a constant approximation even for correlated distributions. Before that, I want to emphasize that all the previous bounds were for the independent case, while this one is for the much more complicated case of correlated distributions. In general, there are very few good mechanisms for correlated distributions in any setting, and this one obtains an approximation ratio that is quite close to 1.38, which is what we can achieve in the much simpler case of independent distributions. Okay, so now back to the Bayer offering mechanism. Here the buyer observes his own value B. He can then compute the distribution over the value of the seller given his own value. And using these two, he can make an offer of P to the seller. If the value of the seller is smaller than P, then the seller will accept the offer and there will be trade. The item is transferred to the buyer, and the buyer pays P units of money to the seller. However, if the value of the seller is larger than P, then there will be no trade. Okay, so in order to prove the theorem, we prove the following claim. We prove that for every B, the approximation ratio of the Bayer offering mechanism, where the value of the buyer is B and the value of the seller is sampled from F of S given B, is E divided by E minus 1. And note that this is enough to prove this theorem in order to prove this claim in order to prove the theorem. Okay, this is because the claim shows that for every B, the approximation ratio of the Bayer offering mechanism, conditioned on the value of the buyers being B, is at most E divided by E minus 1. And so if we have this for every B, we also get it for the general case. We want to prove the claim that for every B, the approximation ratio of the Bayer offering mechanism conditioned on the buyer's value being B is at most E divided by E minus 1. And so we fix the value of B, and we let F be the distribution over the value of the seller given that the buyer's value is B. We denote by P the price chosen by the buyer when his value is B. And now we consider the possible values for the seller. And we divide it into 3 different regions. In the first region, the value of the seller is between 0 and P. And here, the Bayer offering mechanism will trade the item because the value of the seller is smaller than P, than the offer. Also, the optimal allocation will trade the item because the value of the seller is smaller than B, the value of the buyer. In the second region, the value of the seller is larger than B, and here the Bayer offering mechanism will not trade the item because the value of the seller is also larger than P. And the optimal allocation will not trade the item as well because the value of the seller is larger than B. Now in the final region, the value of the seller is between P and B. And here the Bayer offering mechanism will not trade the item because the value of the seller is larger than P. However, the optimal allocation will because the value of the seller is still smaller than the value of the buyer, B. So this is the only case where the allocation of the buyer offer mechanism is different than the optimal allocation. And so this is the only case that might be problematic. So we'll focus on it. We consider the case that most of the mass of the seller's distribution is between P and B. Now, if we show that the expected value of the seller when his value is between P and B is not too small, then it will mean that the buyer offer mechanism has a good approximation. Okay, so we assume that this is not the case. We assume that the expected value of the seller when his value is between P and B is small. And so it means that there exists a point, P prime, that is close to P, that has a high CDF. So most of the seller's distribution is going to be smaller or equal to P prime. However, this will mean that the profit of the buyer from setting an offer of P prime is larger than his profit from setting an offer of P, because P prime is close to P, but it has a much higher CDF. So this cannot be the case. Now we are going to do this more formally and by an example. Let P be equal 0 and B equal 1. We let f of 0 be 1 over E. And now, for every P prime, the profit of the buyer from setting an offer of P prime is going to be smaller or equal to his profit from setting an offer of 0. Okay, so this is the profit of the buyer from setting an offer of P prime. This is B, his value, minus the offer times the probability of trade. And this is going to be smaller or equal to his profit from setting an offer of 0. We rearrange this inequality and we get this bound on the CDF of P prime. Now this is an illustration of this bound, where for values in this interval, the bound was larger than 1, so we placed it by 1. Now, if the probability that the value of the seller is between P and B is going to be larger or equal to 0.6, then it means, for example, that it can't be that all of the values are below 0.3. Okay? And we actually show that the worst case for the approximation ratio of the buyer offering is when F is equal to this purple bound. And we call this distribution equal profit distribution, because the profit of the buyer from setting any price between here and here is going to be equal. This is the case that gives us an approximation ratio of E divided by E minus 1. And observe that we get the same approximation for independent distribution, as the case that we consider where the value of the buyer is 1 and the value of P is 0 fits also the independent case. Okay, so in order to prove the theorem that the approximation ratio of the buyer offering mechanism is at most E divided by E minus 1, even for correlated distributions, we wanted to prove the following claim. We wanted to prove that for every B, the approximation ratio of the buyer offering mechanism, where the value of the buyer is B and the value of the seller is sampled from F of S given B, is E divided by E minus 1. And so the worst case for this claim is when the seller's distribution is an equal profit distribution for the buyer. In this case, the approximation ratio of the buyer offering mechanism is exactly E divided by E minus 1. Okay, so now a recap of our results. Previous work considered independent distributions, we consider correlated ones, and we show that for Bayesian mechanisms, we have an upper bound of 1.58 and a lower bound of 1.34. The lower bound is for deterministic mechanisms. We define the class of one-sided mechanisms that are mechanisms that are dominant strategy for one agent and Bayesian for the other. And in this class, the buyer offering mechanism is the optimal mechanism for correlated distributions, because we have a matching lower bound of E divided by E minus 1. Also for dominant mechanisms, dominant strategy mechanisms for both agents, we cannot get a constant approximation to the welfare. for correlated distributions. Now I'm going to mention some of the open questions that arise from our work. The first one is, what is the best approximation ratio for correlated distributions? So here we know that the Bayer offering mechanism provides an approximation ratio of 1.58, but we want to know if this is the best possible. Okay, so dominant strategy mechanisms cannot help us here because they have an unbounded approximation ratio. One-sided mechanisms are also not enough because we have a lower bound of 1.58. And so if we want a mechanism with a better approximation ratio, it has to be a Bayesian mechanism. And here we have a lower bound of 1.34 for deterministic mechanisms. We are also interested in understanding the power of Bayesian incentive compatible mechanisms. As first of all the mechanisms that are known in the literature are at most one-sided mechanisms. And so we want to know what Bayesian mechanisms look like. It can help us solve the first question, but also for independent distributions, the currently best mechanisms for welfare are dominant strategy ones. And so we want to know what can we do using a Bayesian mechanism. We are also interested in understanding the power of randomized Bayesian incentive compatible mechanisms, as our lower bounds are for deterministic ones. And finally, a natural question is, what can we do for the gains from trade for correlated distributions? Okay, so that's it, and thank you for listening.